dobry Państwu. Witam Państwa bardzo serdecznie na Wydziale Fizyki, Astronomii i Informatyki Stosowanej Uniwersytetu Jagiellońskiego. Chcieliśmy Państwa dzisiaj zaprosić na wykład profesora 𝗍𝗲𝗄𝗵 Forshawa pod tytułem Czarne dziury, klucz do zrozumienia Wszechświata. To jest również tytuł książki wydanej niedawno przez dzisiejszego prelegenta i przez profesora Briana Coxa o tym samym tytule. Wykład będzie po angielsku. Po tym wykładzie będziemy mieli możliwość zadawania pytań, to znaczy zaplanowaliśmy krótką dyskusję, w którą chcielibyśmy Państwa wciągnąć. Proszę Państwa, profesor 𝗍𝗲𝗄𝗵 jest profesorem fizyki teoretycznej, dokładnie fizyki cząstek, na Uniwersytecie w Manchesterze. Jest też bardzo dobrze znanym i wyśmienitym popularyzatorem, autorem wielu książek, produkcji telewizyjnych, osobą, która za popularyzację otrzymała bardzo prestiżowe wyróżnienia w Wielkiej Brytanii. Powinienem dodać, że nie były to wyłącznie wyróżnienia za popularyzację, ponieważ profesor Forshaw jest również wybitnym fizykiem, autorem bardzo wielu specjalistycznych prac, które również były docenione na takim samym poziomie jak jego popularyzacja. Proszę Państwa, ja nie będę przedłużał. Oddaję głos naszemu dzisiejszemu speakerowi i zapraszam Państwa na dzisiejszy wykład. Jeff, the floor is yours. Please.
Thank you. Well, thank you for that very kind introduction, or at least I hope it was a very kind introduction. So it's lovely to be here. I've collaborated with Polish physicists for over 20 years now, including with 𝗍𝗫𝗵𝘄, who's here, and Andrzej Szodmok, who's a professor also in the department. But this is my first trip to Krakow, and I have to thank 𝗍𝗫 for his hospitality today. I got to look around the city, and yeah, it was a very beautiful day. I enjoyed it very much. I'd also like to thank Anna as well, who's been organising things. So thank you very much, Anna. So I think one of the main missions of the talk is to explain to you why the subtitle of this book is not Ridiculous Hyperbole, and why it is that black holes really are important in a very fundamental sense. So I am a theoretical physicist, which means I'm not allowed anywhere near any apparatus. I try to develop theories of the universe and confront the calculations that I perform with data from experiments and observations. My interest in black holes, I'll say a little bit about what black holes are and so on, it is because of their importance in challenging theoretical physics in a way that no other topic does. So there's something very, very unusual, very difficult about black holes. And in the end, it looks like the resolution to that is profound in the sense that it challenges us to make statements about what space is. So you'll see in the course of the talk that I'll be asking a question like, what is space? Like, what actually is it, right? So this is space, the thing that I'm waving my hands around in now. Right, there's kind of up and down, left and right, forwards and backwards. The ideas coming from modern research in black hole physics suggest that space may not be fundamental, but may be constructed, built of something more elemental. Now, it takes a bit of time to think about what that actually means. Right? We're so fundamentally, wrapped up in the idea of space, we take it for granted largely. I'm moving through space. Now, the idea that the thing that I'm moving through is not fundamental in any sense, but it is actually constructed from something else which exists outside of space. I mean, maybe try to think about what that means. What does it mean to talk about things that exist that have no location? A bunch of things, and the relationships between the things gives rise to the thing that we feel as space. So hopefully by the end of the talk, you'll see what I mean by that and why it is that thinking about black holes has pushed us to be thinking in such remarkable terms about the nature of the universe. This kind of thing is why I love doing theoretical physics. It's really a celebration of the universe, an attempt to try to make a connection and understand what is happening in this cosmos that we live in. And black holes certainly a great way of gaining a lot of information, getting a lot of understanding about the way the world works, the way the universe works. So let me start just by explaining what black holes are. For a long time, after Einstein wrote his theory of general relativity in 1915, it didn't take very long, by the way, for people to, it took a few months, in fact, before Carl Schwarzschild had actually found the solution, which we call the black hole solution. The Schwarzschild solution is called today. It took him a few months. Einstein was shocked by how quickly he managed to do that. And he did that whilst working as a soldier on the Eastern Front in the First World War. So really remarkable achievement. So at that point, black holes were conjectured. Like they appeared to be allowed by Einstein's general theory of relativity. Now we've measured them, and in fact, we've seen them. This is a picture of two black holes. This one on the right was discovered second. There are only two photographs of black holes in existence. These are the two. And this one is the one in the center of our Milky Way. So it's 25,000 light years from us, right? Which means that light has been traveling for 25,000 years from that image into the telescope that measured it, the Event Horizon Telescope. The diameter here is about the same as the Mercury's orbital diameter, right? So this is a supermassive black hole, right? Its mass is about 4 million times the mass of the sun. Okay. This one was the one that was seen first, and it was seen first because it's more than 1,000 times bigger than this one, even though it's also about 1,000 times further away. But it's rather easier to see. This one's obscured largely by all the stuff between us and the center of the Milky Way, all the stars, whereas this thing is easier to see. Somebody asked me what I thought about these images when I first saw them, and apart from the obvious joke that they're a bit blurry, was really that the scale of these things, right? So this thing is 6 billion times the mass. So bear this in mind when I talk about what a black hole actually is. This is 6 billion times the mass of the sun, and the light from here set off on its way 60 million years ago. The light that we're now imaging, that we're now seeing. And this diameter is the diameter of the entire solar system. So these are supermassive black holes, which means their masses are millions or billions of solar masses. They're formed most likely out of giant collapsing clouds of hydrogen gas that just collapse in on themselves. The most common source of black hole in the universe isn't made that way. It's made when big stars meet the end of their life. So stars like ours, our star, which has a mass of 1 solar mass, it will not, when it dies, it will not, which will be in a few billion years, fortunately, right? It will not turn into a black hole. So stars that are a few more times heavier than that will collapse into a black hole. So what happens? So the star, like our sun, it keeps itself big by generating pressure due to burning hydrogen and helium in its core. So hydrogen fuses, it's nuclear fusion power, the kind of thing that we're trying to exploit in order to generate power on Earth. Hydrogen fuses to make helium. That generates heat, which then supports the star against collapse. So the star does want to collapse in on itself because of gravity, which wants to fall in. But the pressure from the thermonuclear reactions is preventing that from happening. But of course, that fuel will run out, and when it runs out, the star collapses. And in the case, there are two possible situations where the collapse is halted. So if the star is not too heavy, the star can collapse down into, I could talk about white dwarf stars, let me talk about neutron stars. So it stops, the collapse stops, and forms a neutron star. There are lots of neutron stars in the universe. One great way of detecting them is by measuring the radio waves they produce when they spin around. They kind of beam out radio waves, and that can be detected by a radio antenna here on Earth. So lots of neutron stars have been seen. A teaspoon of neutron star matter weighs the same as a mountain. So these are very, very dense objects. So if you think about, like, what does that mean? That you can collapse something, squash something down into a very small region of space. We have a sense of things being rigid. It seems inconceivable that we could squash even that table down into the size of a peanut. I mean, that just seems like a ridiculous idea. But we're now talking about collapsing an entire star into a region potentially smaller than that. And that's okay. That is allowed. Fundamental physics teaches us that, in fact, the entire observable universe once occupied a region of space which is far smaller than the size of a single proton now. And the entire observable universe contains billions of galaxies, which contain billions and hundreds of billions of stars. So, I mean, one thing, this is not what I'm going to talk about, but for sure, what we've learned about the cosmos and about the stuff it contains is that the apparent kind of puffed out nature of matter is very much an illusion. That we're really, if I could really see, in some sense, the floor that I'm standing on, I'd get vertigo. It would be, I'm basically standing on nothing. There is, even basic physics tells you that in a hydrogen atom, of the atomic nucleus, imagine the atomic nucleus of a hydrogen atom, the simplest of all atoms. Imagine zooming in so the nucleus is the size of a pea, then the electron that orbits that is at a distance of a few hundred meters away. So that's typical of atoms. It's like a little grain of sand orbiting a pea. And atoms are largely empty, but that's not the half of it. We can really scrunch things down. Black holes occur when the matter is sufficiently heavy that it doesn't stop with a neutron star. The mass is sufficiently heavy that in a neutron star, what pushes back is an effect in quantum mechanics due to the Pauli exclusion principle, which, if you know a little bit of chemistry, you may know about, that electrons don't like to be pushed on top of each other, or fermions. In the case of a neutron star, it's the neutrons don't like to be scrunched too much. They kind of push apart. But if the mass is large enough, that won't save the star, and it will collapse to nothing. It will collapse and disappear. That's what a black hole of a few solar masses is. It's the end point of a star. Now, we've seen collisions, I say seen in quotes now, we've measured collisions between black holes. So this is a recent thing in the last 10 years or so, where we've measured collisions between black holes. Two black holes collide, and in so doing, they kind of spiral in around each other, collide, coalesce to make a big black hole. And that generates a lot of energy, which can be measured here on Earth in the form of gravity waves, which are kind of waves in space, which is a very strange idea, which cause, on Earth, the experiments that measure them have got mirrors, which are about 1 kilometer or so apart, and those mirrors move, on average, by distances which are far less than the diameter of a single proton. And these experiments, these mirrors are 1 kilometer or so apart, and we can measure the mean separation of the mirrors, I say we, certainly not me, to that kind of precision, and pick up these collisions. Not just trigger that they've actually happened, but actually understand what the dynamics of the in-spiral was. So that's a topic of physics. I'm not going to talk about that. These are observational matters, right? So here's an observational matter. The detection of black hole mergers through the gravitational waves they produce. There's no doubt that black holes exist now. So let me move on now to the theory of black holes. Right? There's not much fundamental theory that we need to understand in order to get a real picture of what a black hole is, but this is one. So this is Einstein's general theory of relativity in a slide. Right? The basic idea is that space can be warped, and time for that matter. And so that sounds like, what does that mean? Space can be warped. Right? Well, it sounds like a strange idea, but in fact it's something that we're all quite familiar with, in fact, because we live on the surface of the Earth. So let me get you to imagine something, because this will be a useful thing for a couple of slides coming up. Imagine that you're flat, completely flat, and you can slide around on the ground. Right? So you have no notion of up and down. I'm making that simplification, because if you do that, in your mind's eye, you will be able to visualize the idea of curved space. Trying to visualize curved space in 3 spatial dimensions is impossible. Our brains have just not worked out how to do that. The mathematics is exactly the same. So the analogy is not some kind of metaphor, it's a very precise analogy. So imagine you're squashed onto the ground. You can slide around, you can move forwards and backwards, left and right. So if you slide around on this floor, imagine sliding on the floor here, right, a flat creature that slides around the floor. You could trace out a right-angled triangle, and the length of the hypotenuse on the triangle would be, the squared length would be the sum of the squares of the other 2 sides, if it's a right-angled triangle. So Pythagoras' theorem, you would confirm it. Right? And if you and your friend went in parallel lines along the floor, you wouldn't meet. So that would be, except you would meet, right, if it really was a ball that you were on. Right? Imagine that you and your friend are on the equator of a ball, traveling to the North Pole. You'll actually come together and cross at the North Pole. You can also trace out, so parallel lines do, in fact, though parallel lines, every point you're doing this, moving forwards, precisely forwards. You're not swerving, but you and your friend will join together at the North Pole if you started off walking due north from the equator. Can you picture that? So that, likewise, it's possible to draw triangles on the surface of a ball whose interior angles add up to all kinds of numbers, but including up to 90 times 270 degrees. So 3 right-angled triangles in a triangle on the Earth. Come around the equator, up to the North Pole, back round against the equator. Always a right angle. So the geometry of a curved space is like that. That's if you may be thinking, well, actually, the sphere, the 2D sphere, I can imagine it embedded in 3D. So I know that really there's a straight line, but the straight line comes off the sphere, right? But if the sphere is the space, if the entire space is the sphere, it makes no sense to talk about things coming off it. So the geometry of the space can be non-Euclidean. That's to say, it doesn't satisfy Euclid's axioms. Parallel lines can meet. Straight lines, right, appear curved when viewed from a higher dimension. But the higher dimension doesn't actually have to exist. So that is what Einstein said our space is like, our 3D space. The axioms of Euclid do not generally apply to to objects moving around in the presence of gravitating matter, right, which basically is anything with energy. So here I've got like a picture of the Earth, and it's symbolically shown, the mass causes the space, which is drawn here as the graph paper, to distort, and consequently we can have interesting planetary orbits, for example, our free fall. That's something that's always traveling in a straight line in a curved geometry. So that's idea number 1, right? This is my picture of a black hole. I like this picture. Yeah. So there are a couple of important points here, right? So this is a first approximation to a black hole. So that picture of the black hole that I showed 2 slides ago, which is the photograph, had got lots of bright stuff around it, right? That's gas going into the hole or moving around it. And as the gas accelerates into the hole, it radiates light, and we see that light. Okay? So if there would be no gas around a black hole, we wouldn't actually be able to see it. Right? So it would be featureless, and if it was face on, we'd see this featureless black disk. So what is the significance of this black disk? Right? There are two things. The important point that there are 2 things I want to talk about. One is that there is an edge, there is a black disk, that this is the black hole. There is something in space. It's like a black sphere. If the black hole's rotating, it's not quite a sphere, but it's got something which we'll call the horizon of the black hole. And if you are here, you're in a little spaceship moving around the hole. You can go into orbit around the hole if you want. Black holes don't suck things in. Their gravity is just like the gravity of the sun. Right? So outside, you can go into orbit, or you can kind of jump in. But if you jump in and go inside this disk, you can't get back out again. Nothing can get back out. So if I jump in here and then shine this laser pointer out, the light from the laser pointer never gets back out again. The gravity is just so strong inside that nothing can escape from this interior region. So stuff that fell in to make the black hole, right, the picture looks like it's all going to come together to a point in the middle. We're going to see that it's much more interesting than that. Right? So I'm going to talk about the middle of the black hole in a minute, but you can see something like quite dramatic is happening. If this black hole was formed by a collapsing star, it's like the material, there's some point where the star's density has gone to infinity at the middle of over here. That is the origin of much of the problems that we've got in understanding how black holes work. It's like we've tried to compress an entire star into nothing. And that's what happens to make black holes. So we're going to talk about that in a second. But the horizon is going to prove out to be really important to us in what follows. Right? So there is something called, I might use the word equivalence principle in what follows. If I do, what it means is that it's the basic idea that if I'm floating in outer space, I don't feel gravity, which is a fairly obvious statement. Or if I'm falling near a star, I don't feel gravity either. In fact, if you just fall off the roof of a building, if it weren't for air resistance, you would feel like you're floating. Right? That's a very profound idea, and it was Einstein who really appreciated its profundity. I think in that context, he tells the story of watching somebody on ladders, and he imagined if they, rather like sinister, like he imagined them falling off the ladder, and realized that actually if it weren't for air resistance, their experience would be the same as somebody floating freely in space. And it's a fundamental property of Einstein's general relativity. Einstein's general relativity respects that principle. And so anybody just falling through the horizon of a black hole wouldn't necessarily feel anything at all. In fact, if the black hole is very big, in fact, if the black hole is sufficiently big, we could be falling through the horizon of a black hole now. Nothing remarkable happening at all. At some point in the future, because we've gone inside the black hole, we will be exposed to the singularity, and we'll experience that, as we'll see in a couple of slides, maybe the next slide. We'll get stretched out, spaghettified, and we will know that we're in the black hole at that point. Right? But if it's a very, very, very large black hole, that could be a long time away. And so we could easily be, the horizon basically would be flying past this room at the speed of light. That's basically what would happen. So we're here, I'm talking to you, I'm saying we could be going through the horizon of the black hole now. The horizon would just shoot through at the speed of light, and there we are, we're inside the black hole now. Nothing remarkable would happen if the hole was big enough. So that's the first thing. Somebody freely falling through the horizon of a black hole doesn't feel anything dramatic. Right. This is now for the first really weird bit of physics, right? If you're hovering here in a little spaceship right on the horizon of the black hole, it feels very hot. Right? So it's as if the black hole horizon is well, actually of infinite temperature as you get onto the horizon. So you couldn't build any spaceship that would, no matter how much you tried to make it heat-proof, it would not be able to survive close to the horizon of a black hole hovering. It would burn up. I mean, that sounds contradictory to the other case, because one person falling through the horizon feels nothing. Somebody who's trying to sit close to the horizon thinks they're in a very hot place. Okay, bear that in mind, because we're going to come back to that. That's going to cause us some problems. It already sounds like it does, doesn't it? It's how can it be both hot and not hot? Right, so this picture is an attempt to explain a couple of things. This is not actually a picture of any black hole or even a 2D version of any black hole in the universe as we know it. So this thing's going to be a wormhole. This is another universe. This is a universe. So I'm just going to explain what's going on here. Right? Some of the properties of this will be relevant for our black holes. This is two people, and they can slide around. Can you see that I've tried to draw a 2D space? This graph paper type thing is a two-dimensional space. These are two-dimensional creatures that can slide around on the two-dimensional space. They don't know about off the page. We're all happy with that, right? So these two people could slide around to each other and say, oh, look, this is the horizon, by the way, of the black hole. This. Right? They've done enough, maybe they've thrown enough things into the black hole to work out that this is the horizon of the black hole. So they don't want to go past that. Right? But they can walk around it. If one of them did decide to go in, we've got the possibility that they can slide in. This is not possible. I'll explain why in a minute. But from this picture, it looks like they could slide in, slide down here, and pop out. This goes on. I've only truncated it here. Right? This is in this space. I could have drawn these lines going out here forever, right? But the picture would get a bit messy. So what I've tried to draw here is two flat sheets, infinitely big, with a hole in one that tunnels through to the other one. Okay? Now, this person, if their arms were long enough, actually, could hold hands with this person on both sides and kind of encompass the black hole. They could, can you imagine that? If they had really long arms on this picture, they could kind of, and then they could say, look, inside of this circle that we've just made, there's an infinite universe. Because there is. Can you see that there's all this universe here at the bottom, inside? It's because space can be curved. Because space can be curved, it's perfect. Curved space allows for the idea that if I put my hands like this, that the interior space inside my hands could be, if there were a black hole in there of this type, right, there could be an infinite other universe inside my hands because of the curvature of the space. I said that we needed to drop a dimension to go to 2 dimensions in order to picture what's going on, right? Picture how that's possible. Right? It's remarkably counterintuitive, but it's really a fascinating idea, right? So let's stick in the 2D world. This is the 2-dimensional world. We live in a 3D world. Our black hole horizons are spheres. This black hole horizon is a circle. But that's the main difference. Now let's actually imagine that this person actually does jump into the black hole. Then what actually happens dynamically as this person goes through the horizon of the black hole, this, from their perspective, this thing, right, well, not from their perspective, this thing here is stretching out as they fall. This is what happens in this particular solution to Einstein's equations of gravity. So this stretches out. So I imagine we've got one universe here. This is the top. This is where these two people are. They're in this big flat sheet up here, right? There's this, right? There's this bit of the surface. It's a bit like if I had a rubber sheet, I've kind of pulled down this bit in the middle. I've pulled it down, right? And I keep pulling it down as the person slides in. Then the person, can you see that the person is going to get stretched out because I'm stretching this. Stretch, 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 stretch. This thing stretches to nothing. Just before that, this person is basically a complete line of atoms. They've been stretched out so much because the space is stretching. So these are tidal effects inside the horizon of the black hole, which have caused this person to become spaghettified. The singularity is the moment when this basically snaps. It stretches to nothing. Gone. The person that was sliding down here disappears from the universe. That is what Einstein's general relativity is teaching us about what happens inside of a black hole. Do we believe that? Do we believe that that's actually what happens? That this person, or anything thrown into a black hole, meets the end of time. That's basically what I'm saying. And the singularity is the end of time. It's not appropriate. You know, remember that picture that I showed here? It's very tempting to think of the singularity as a point in the middle. Right? But we've seen that because of the geometry of space, right, it's not that. It's instead a moment in time. It's the point where where the interior of the black hole stretches to such a point that the space itself kind of disappears. Okay. So that's the first half of the talk, and it's an introduction to black holes in Einstein's gravity. So I should say that what I've just been talking about, it is the understanding. I mean, when stars are formed, when black holes in our universe are formed from collapsing stars, there's always the star at the bottom here blocking this off. Right? So if a star collapses, and then you jump into the black hole that's formed when the star's collapsed, you'll see the star below you getting smaller, right? And you'll follow it, right? So here's a star. Now the star falls down here, just like you fall down, right? The space stretches, so the star starts getting further and further away from you. So it's getting stretched and put as well. And at the point where you disappear, you don't see the star disappear first. You disappear, and that's that. And the star was moving off to an infinite. At the point where you disappear, the star has been stretched away from you by an infinite amount, a very large distance. It's going further and further away. So everybody who jumps into a black hole formed by a collapsing star has basically got the star at the bottom that is blocking the way through to this region. Okay, so there are no wormholes like this made by collapsing stars, because basically the star blocks the wormhole up. But even if there were solutions like this, it's still not possible to get to the other side because the wormhole snaps before you get to the other side. Okay. Right. Now, none of what I just talked about mentions quantum physics. Right? The second bit of the talk is going to be about quantum physics and how that, and this is you know, it's the intersection of Einstein's general theory of relativity with quantum physics, which is the bit that does the thing that I said I really like and I'm really interested in, that really, you know, it really points to something profoundly interesting about the way, profoundly significant in our understanding of the cosmos. Right? So what? Right? And obviously, I couldn't resist, so hopefully in the next, how long have I got? Next 25 minutes or so, I can convince you that this is not completely ridiculous. I mean, it is ridiculous, but not completely wrong, and that, you know, that it kind of increases we're going to do this first, that space is built from elemental jiggling things, something that follows from the work of Stephen Hawking. So we're going to talk about the book, by the way, is a large part a tribute to the work of Stephen Hawking, and to he triggered the stuff I'm going to be talking about in his work in the early 1970s. We'll come to the idea that the universe is a hologram, right? and that perhaps we are living in something rather like a giant quantum computer, which I stress doesn't mean that we're living in a simulation, although, you know, if I told you that it looks like we're living in a computer. Let me give you just a very, like the idea of living in that the universe is a hologram. I just want to be provocative here. Like, imagine that you actually lived in a computer game, right? A really good computer game, and you worked out that in actual fact there was an equivalent description of you which could be represented by computer gates on a silicon chip. Right? You actually discovered that there was that chip doesn't have all the features of the world in which you live in it. The stuff that you're experiencing is an emergent property of the stuff coded onto the chip. That's the sense in which I'm talking about hologram, in fact. That the world that we're living in is in some sense a projection of some description which doesn't actually involve gravity, for example. Right? So it's like gravity is not, which means space, is not fundamental. It's actually an emergent property that is a feature of this holographically dual theory. Right? So it is very analogous to somebody who writes a computer program in which there are creatures who move around in gravity, even though there's no gravity in the computer program. Right? It's basically coded up. So the creatures think that they're living in a gravitational theory, but they're not. Now, having said that, because I really would not want people to get the wrong impression, I think what that does is at least give a flavor of what I'm talking about. But that doesn't mean that we're living in a simulation, and it doesn't mean that we're living inside of a giant quantum computer. Right? What it likely means, and much more simpler explanation, is that the methodologies that we are currently attempting to exploit to build quantum computers were already exploited by nature. So the way in which the universe is built is analogous to the way in which, right, we might try to build a quantum computer. So solving the problem of quantum gravity, which is what I'm talking about, may be very closely related to the problem of building a quantum computer. So I'll talk a little bit about what all that means. That's kind of where I'm going. So let me make a start on this, and we'll see how far we can get through it. Right, so this is the most mathematical slide of the talk. Right, this is a statement of the laws of black hole mechanics as discovered by Carter, Bardeen, and Hawking in the early 1970s. Right? These, the laws of thermodynamics, developed in the 19th century in order to understand things like steam engines. The laws of thermodynamics, the zeroth law, the temperature is constant in a system in thermal equilibrium. And that's not very glamorous. The first law, the change in energy of a system is related to the change in entropy of a system in direct proportion to the temperature. The entropy of a system is a measure of how much we don't know about the system, essentially. It's a measure of ignorance. It's a measure of how much information I would need to give you in order that you would understand completely the system. The system in thermodynamics, and certainly in a steam engine, is a gas. A gas, right, that does work, drives a steam engine. And the entropy, right, of the gas is a measure of how much we don't know about the state of the gas. So if the gas in this room, the air in this room was all in that far corner over there, that would be a much lower entropy configuration than the configuration that we're in now, where it's across the room. Right? Because the number of possible ways of putting the gas into the corner of the room is far less than the number of ways of arranging the molecules in the room to make the gas in the room. Can you see that? It's like, you could say the gas is definitely over there. It's all over there. It's all in this tiny little region. All the atoms are in that little corner. Whereas in this bit, where's one atom? Any one atom could be anywhere. It could be in that corner, that corner, that corner. We do not know. It would take a lot of information to tell us where all the atoms were in this room. Right? Much more information would be needed to describe the gas in this room than the gas if it was just in that top corner of the room. That's entropy, right? And it increases, right? right? So the second law of thermodynamics is basically a statement that entropy, for any closed system, entropy will increase. Okay. So this is basically the way we see it in everyday life, is that it tends to be, it is the idea that if we that light in that top corner of the room there, that light, that gas in the top corner of the room, if we leave it, it will spread out and fill the room up, right? And increase its entropy in so doing, right? It won't go the other way. All the air in this room is very unlikely to end up in that corner over there. That's the statement of the second law of thermodynamics. It's very important because the consequence of this is that heat doesn't flow from cold things to hot things. It flows the other way. It flows from hot things, high temperature things, to low temperature things. Right? Heat could go the other way and not violate the law of conservation of energy. You could take heat out of a cold thing and put it into a hot thing. Right? That's how a fridge works. Right? But a fridge does it because it's plugged in at the wall. There's an external supply of power which allows it to do that. Right? Under normal circumstances, if the fridge is not plugged in, the fridge is not spontaneously going to cool down. Right? Even though energy conservation by itself does allow for that to happen. So that's the second law. Right? And then the third law is the statement that it's impossible to actually cool a system down so that the temperature reaches absolute zero, which is minus 273 point something degrees Kelvin. Okay, this column here is a statement of the laws. The proof of these results using general relativity, which is all that's needed to prove these results, is not a simple thing. Right? So this was something of a triumph by Bardeen, Hawking, and Carter that they derived these rules. But you don't need to be a mathematician to see that there's a similarity here. Right? Can you just change the words and the symbols? Change T for K. T, K. Right? Change S for A. S, A, S, A. There's T and K again, T and K. Right? When they wrote that paper originally, the laws of black hole mechanics, they thought that they'd just discovered an accident. Hawking then, the reason they thought it was an accident is because they were pretty sure that the black holes don't have temperature, because they don't emit anything. Anything with temperature emits. That's like a hot coal radiates. I'm radiating in the infrared now, so you've got infrared goggles on, you can see the radiation that I'm radiating, and that you are as well. So everything with a temperature radiates, because the atoms are jiggling around and that radiates off electromagnetic radiation, light. So the atoms are jiggling around and it radiates, but a black hole doesn't have, it's not made of atoms and it's not radiating anything, so its temperature is zero. And that's what they thought, that's what everybody thought. Then Hawking discovered that they do radiate, they do actually emit. Quantum mechanics allows for black holes to radiate. It's tiny, nobody's ever measured the radiation from a black hole. It's very, very small, right, for all the black holes that we're looking at. It can become intense when the black hole becomes very small, but we're not there's no prospect of being able to detect this radiation, but it does mean that the black hole will basically evaporate away because it's losing energy to this is called Hawking radiation that I'm talking about. So black holes do have a temperature, right? And Hawking's calculation, a paper called Black Hole Explosions, he actually calculated what the temperature was, and he confirmed this, that the temperature is essentially the surface gravity. So at that point, he in what was a very understated conclusion to that paper, he said, when Bardeen, Carter and I wrote the laws of black hole mechanics down, we thought that the analogy with thermodynamics was just a coincidence. And then the paper concludes with the statement, seems that there's more to it than this, which is a very, and that we should perhaps say that the surface gravity is the temperature of the black hole. That's what Hawking has said. But temperature is a property of things that are made up of little things jiggling around. That's what temperature is. Entropy is a measure of ignorance. It's all that, things with entropy are made up of lots of little bits and pieces whose arrangement we don't know. Right? But surface gravity and the area of a black hole are geometrical quantities. They're geometry. They're properties of space. So this This is very profound, right? This is saying that the geometry of space appears to be an average type of feature of things, a consequence, an emergent consequence of things jiggling. What? Since we're talking about the geometry of space, the suggestion is that space itself is built of something that's more fundamental and jiggles. And that was appreciated by people at the time, but it's laid dormant, that idea, in that, I mean, string theorists. So the big question then would be, what are the tiny jiggling things? What are the little jiggling things that give rise to space, right? And that's been a challenge for theoretical physicists ever since Hawking and collaborators established that the laws of black hole mechanics indicate that gravity and thermodynamics are in fact one and the same thing. Right, so this is actually Hawking's expression for the temperature of a black hole, and this is his tombstone in Westminster Abbey in London. So here's a picture of some Hawking radiation coming off. Now, things get fun now. We've got the pace can increase a little bit, right? We're going to get now to the idea that if this is going to cause problems, if a black hole can radiate off energy, it will shrink and eventually evaporate away. Which really begs the question as to what happened to all the stuff that you threw in, right? Which kind of disappeared in the singularity. While the black hole is still there, you can at least say, well, it went into the singularity, but I have no idea what the singularity is. So, presumably, I'm just not smart enough to know what happens to things that go into the singularity of a black hole. Maybe things change a bit there. Probably they do, almost certainly they do, right? But you can't hide behind that argument if the black hole actually disappears. It's gone. There is no singularity. When the black hole is evaporated, the place where the black hole was is featureless again. It's like it had never been there at all, and all that remains is the radiation that came off. So now we do have something to think about. This is the black hole information paradox. This picture is, I should mention it, I'd forgotten to mention this. The idea, here, that the entropy of a black hole is proportional to the area of the horizon is very unusual. So I told you that all you need to know about the entropy is how much information I need to give you to specify the complete state of the system. So stuff thrown into a black hole, right? All the information about everything that got chucked into this black hole, right? It's got entropy, right? It's the stuff that we don't know about the black hole. Presumably that includes all the information about the stuff that got thrown into the black hole. Right? But the idea that entropy is proportional to the area of the black hole is like, what? The information in something you would normally think of as being proportional to the volume of the thing, or at least, it's the information content of a thing is all the bits and pieces that make the thing up. The idea that the informational content of a black hole is encoded on the surface of the black hole is odd, right? And that's what this picture here is getting us to think about. We'll come back to this, because this is the beginnings of this hologram idea, right? This is an encoding of the information, a schematic of the encoding of the information in a black hole, right? And it looks like it's tiled on the horizon of the black hole, right? The information here is contained in all of the information in the black hole. Presumably, it's got all the information about what's going on inside the black hole. So the idea that the information on some region can code for the information in the interior of the region is where we're going. Like, for example, the idea that the informational content in this room, which is like what you're doing now, or whatever, what we're all doing, there's a lot of information about what is happening in this room. The idea that information is in some sense encoded on some surface surrounding the room, or equivalently, it's like a library that all the informational content of a library is not in the books inside, or well, it's dual. It can be in the book. It is in the books inside, but it's also represented on the walls of the library, in some sense. What does that like? The idea that there can be a holographic description of an object, right? That's to say, we can describe the physics. So in this case, the physics of a three-dimensional object in terms of information on a 2D surface. Right? It's like that third dimension looks like it might be redundant. Let's see, bear that thought in mind, because we're going to come back to it. Right? So the information paradox is pretty much what I've just been saying. Let me just put it in context. This is a book, this is a fire, and these are the ashes afterwards, and all the molecules that have come off in the combustion process. Right? In principle, this process doesn't destroy information, technically. Right? It certainly destroys it practically. You know, we've no hope of being able to reconstruct the book from all that junk. But in principle, the information has just been transformed, right? From book to, like, burnt book, right? Nothing's been completely obliterated. Now, the black hole case is somewhat more intriguing, because I throw the book into a black hole, right? Okay, this book, right? The information is lost forever, right? The black hole evaporates to nothing. No. It was Stephen Hawking who did the original calculation, which has stood, and it took a very long time to work out, and we still don't understand properly how this works. But Hawking's statement was that the radiation that comes off bears no resemblance, is not related to the, you know, you can't reconstruct the book from the radiation. Right? So the radiation is featureless. Right? You chuck the book in, radiation comes off, the radiation at the end is featureless, the book has been utterly destroyed. There is no means ever, in principle, of recovering the information in the book. Fundamentally different idea. In this case, the information has just been obliterated and made extremely difficult to get access to. In this case, it's gone. Is that really what happens in physics? Right? So this was the black hole information paradox. There are a lot of reasons for supposing that really this does not happen. This can't happen. The information must be coming out in the radiation. And we now understand that that is the case, thanks to calculations over the last few years. Right? But let's see how we got to that state, right? How we got to the position of making the statement that Stephen Hawking was wrong. I mean, Hawking actually admitted, the development where he appreciated that the information must come out in the radiation, that development occurred during his lifetime, and he accepted it. So we'll get to that. Here is the beginnings of the problem, right? Here's the book. It's thrown into the black hole. Let's think about what happens from the perspective of somebody in a spaceship hovering outside the black hole. I told you before that somebody hovering close to the horizon of a black hole sees the horizon as a very hot place. Right? So the book, and I told you that the book never goes through the horizon. So throw a book into a black hole and stand outside hovering in a spaceship. It's hot, right? The book never falls through the horizon, right? Very natural to suppose that the book gets burnt up and the information content of the book basically comes back out again in the radiation from the evaporation of the black hole. That's a very reasonable thing for us to conclude. So the information comes out, the book's burnt up on the horizon. Now from the point of view of the book, it's the same book, it falls in. Right? From this person's point of view, it never actually passes through the horizon. It takes an infinite amount of time to actually pass through the horizon from the point of view of this person. And this is very strange. This is when I said that it's a consequence of the fact that the geometry of time is basically impacted by, in general relativity. The same book goes through the horizon. Don't fall through with it. I don't know why I picked a house. Right? You fall through the horizon with the book. What will happen to you as you head into the singularity? Well, we know from what we've just been talking. You get stretched out and spaghettified. You and the book will disappear, like as space gets stretched out to nothing. So the demise of you and the book here is spaghettification. The demise of the book here, because remember, the black hole can disappear, can evaporate in a finite time. There is this person who's, obviously, they have to live for a near infinite number of years to be able to see this, but never mind. They're hovering here, right? The black hole evaporates away, disappears. Right? The book never actually fell through the horizon of the black hole. Right? Right, in this case, both us, the person falling through the horizon, and the book got spaghettified. What actually happened to the book? Imagine if the book had feelings. What would it say happened to it? Right. If the information does get out, in this case, the book goes onto the horizon, gets burnt up, and comes out. If it goes in here, at the end, both situations must be both universes are the same universe. There's not two universes with two different descriptions. This is one universe described from two different perspectives. But in the long future, the black hole's gone. There's only the Hawking radiation that came out. Which was it? Collect the Hawking radiation, get the book. What will you learn? That the book burnt up on the surface, or that the book fell in and got spaghettified? The answer no is that you'll learn it could have been either. Both occurred. So this book, it doesn't make sense to say that this book, its fate is to get burnt up on the horizon, or that it gets spaghettified as it falls through into the black hole. How is that possible? Now, maybe the connection with the holographic description now starts to look a little bit more. Remember, the idea that whatever is happening in some region is also equivalently described on the boundary to the region. That's sounding like we could win this. We could get a win-win situation. The theory that describes the burning up of the book also describes the spaghettification of the book. That there are two interpretations of the physics, right? Now that idea, remarkably, that idea came without much more direction or evidence than I've presented now. It was developed by Gerard 't Hooft and Leonard Susskind, right? So the idea of holography was introduced by these guys, but it became taken really seriously following the work of Juan Maldacena, Argentinian theoretical physicist. The paper that he wrote on this is now the most highly cited paper in theoretical particle physics, full stop. Right? It's got, 20,000 citations, something like that. 20,000 other papers have been written on the back of this. It's changed the face of theoretical physics. Basically, Maldacena confirmed this. He confirmed that this is basically on the right track. And he did it in a universe that's not our universe. But that's okay. It's very common for theory. If a problem is too complicated, simplify it and then calculate in the simplified theory. It's like everybody does that. People who are building bridges do that, right? They don't know every detail about a bridge, but they know enough to be able to build a bridge such that it won't fall down. Right? Now, admittedly, Maldacena's construction was quite a bit different from our universe. Right? So it was not even as simple as the picture that I've drawn here. But let me give you some sense of what and yes, Maldacena's idea has since been confirmed in a situation very similar to the one I've drawn here. Right? So this is the universe. This disk at the bottom is the universe at some early moment in time. So already it's a bit weird. It's a 2D disk. Right? Actually, the boundary of the disk, all these little shapes on the disk here, they're all the same size. So this is a projection of an infinite space. You can see that the little triangle things get smaller as I go towards the edge. This is called a Poincaré disk. It's a representation of two-dimensional hyperbolic geometry. Right. So, and then this disk up here is the universe, is space at some later time. So, if you like, and then I've got time running up here. So this is a representation of the evolution of this universe. So these arrows represent, just schematically, some matter that's collapsing to make a black hole. The black hole forms there. This is the event horizon of the black hole. So the edge of this, can you imagine this is like a cigar shape, and the circle going around that cigar is the horizon of the black hole. Think of it like that. Then this is the Hawking radiation coming off, and this is the black hole disappearing again at some late time. So I'm simplifying, but not in essence, right? The idea is that this whole process, it's physics, this is gravity physics. You know, something collapses, makes a black hole, evolves, evaporates. There is an equivalent description of all of this. This is what Maldacena showed. There is an equivalent description of this, right, in terms of a theory that only lives on the boundary of the disk, and that theory is quantum mechanical. It's just quantum mechanics, there's no gravity in it. So it's a one-dimensional, because the boundary of the disk is one-dimensional, so the boundary of this can, if you like, right, these circles, it's a one-dimensional spatial circle, right, and one dimension in time. So this would be regarded as a 1 + 1 dimensional theory, quantum mechanics theory. No gravity in it at all. It's equivalent to the disk is 2D, a 2 + 1 dimensional gravity theory. So gravity emerges as a consequence of quantum mechanics. It's basically the content of the holographic principle. So the information in the interior is encoded on the boundary, which is exactly the kind of statement that we were pushed into by thinking about black holes. For the last 5 minutes, have I got 5 minutes left? Yeah. For the last 5 minutes, I'm not going to talk about black holes. I'm going to talk about how that works. This is the way we now make connection with, this is the holographic bit. We did the jiggling things when we talked about the black hole, the laws of black hole mechanics. We're going to finish off by how does it work, that? How do you get to do that? How do you build a system that is holographic like that? You know, so that the theory on the boundary encodes for the interior. That's what we're doing, right? The boundary of this circle that surrounds the disk, a quantum theory on that boundary, right, can be used. Understanding that theory is sufficient to understand the gravitational physics in the interior. The interior theory is 2 space dimensions. The boundary theory has 1. Right? So we've just made an extra dimension of space just by considering quantum mechanics in a theory of lower dimensions. It begs the question, can we make all of our dimensions in space by considering quantum mechanics in a zero-dimensional theory? Like, is it that space is actually constructed as it's an emergent feature of quantum mechanics? By space, I mean gravity. Right, I'm going to finish. Actually, let me spend 1 minute on that previous slide. So, because I need to introduce the idea. So I'm going to draw attention now to the similarity with quantum computing. Right. So in an attempt to understand how holography works, how does this Maldacena idea play out? Right. A lot of people subsequently attempted to understand what's the essential physics. And what they appreciated, this picture here is due to a Canadian physicist called Brianem Coxem, who presented this in a very simple-minded way, which I'm going to use. So the idea here, this is a sphere, right? Imagine that we've got a quantum theory of imagine a gas on the surface of the sphere that interacts. So the particles of the gas are interacting with each other. Now, there is a feature of quantum theory called quantum entanglement, which is exploited in building quantum computers. So a quantum computer, just to illustrate what's so cool about a quantum computer, the state of a classical 4-bit computer could be a number like that. It's a string of 4 digits, either 0 or 1. That, of course, every mobile phone, every computer that we've got is basically a manipulation of strings of binary digits. That's how using operations on those digits in order to build the function of the computer, mobile phone, whatever. It's etched on silicon, it's processing these things. A 4-qubit computer, so quantum bits can be both 0 and 1 at the same time. That doesn't make sense. That's like saying a switch can be both on and off at the same time. Makes no sense in any classical sense. It means that a cat can be both alive and dead at the same time, to use Schrödinger's example. So, but it does mean that the state of a 4-bit quantum computer can be any state in super. So this is the state of one of the possible states of a 4-qubit quantum computer. It can be all these things at once. There are 16 there because 2 to the power of 4 is 16. That's how many possible states there are. The quantum computer can be in all these states at the same time. That's very good from the point of view of being able to potentially exploit as a computing device. A 300-qubit quantum computer, right? This is a 4-qubit quantum computer. It's got 2, 4, 8, 16 states. 16 states. 2 to the power of 4 is 16. 2 to the power of 300, so just a 300-qubit quantum computer. That's all. I think the world record is actually close to that now. That number of qubits, 2 to the power of 300, is more than there are atoms in the entire observable universe. So you couldn't even represent the state of a 300-qubit quantum computer, even if you had a computer, a classical computer, like the ones in our mobile phones, which was as big as the entire observable universe. So there's a lot of informational capacity in quantum bits, right? This is an entangled state. These are all entangled. Well, it's not. Yeah, it is. Yes, it is. This is an entangled state. So if we entangle, imagine a bunch of qubits on this sphere. If we entangle the qubits on the left and on the right, the more entanglement there is, right, the larger the disk that separates the two halves of the sphere. So if there's less entanglement, something more like this happens. So can you see that the amount of entanglement on the surface controls the geometry of the interior? That's really cool, right? Quantum entanglement on the surface changes the geometry. If you take away all the entanglement altogether, there's no way of getting from the left to the right. Right? It's like space is woven out of quantum entanglement. That's what it looks like is happening. And this is the last slide now. Right, so this is actually a quantum error correction code. It's also an example of a holographic system. Each of the circles is a qubit. The pentagons are what are called error correcting codes. So in here we've got like 3 qubits feed into this pentagon. This red one is another qubit, right? There's a 4th qubit. The other qubit comes out and feeds into this pentagon, right? So 1, 2, 3, 4, 5, 6 qubits, right? We network all these qubits, and we network them in this pattern. It's the pattern of the Poincaré disk, in fact. Right? So these don't have to be small on the edge, right? I've just drawn them small in order that I can show you the pattern. You can imagine this pattern going on all the way out to the edge with ever smaller pentagons. But even if you stop at this level, just with a few layers like this, then what this system has got is the property that if I start to destroy qubits on the boundary, this is a network of qubits. This is like what a quantum computer might be like. It's a network of qubits, but if I destroy qubits on the boundary, right, I don't necessarily destroy the red qubit in the middle. So I can destroy large portions of the boundary without destroying the qubit in the middle. That is a vital component in the construction of a modern quantum computer, because quantum computers basically stop working very easily because of their interaction with their environment. Right? So what you want to do is encode the information, in this case the information in the middle here. You want to encode it in a way such that the information is, you encode the information such that you can wipe out or lose large bits of the boundary, but you still don't lose the interior. Right? So that's an error correcting code. That's of great utility to people who are trying to build quantum computers. Right? They want to work out how to network together qubits in such a way that the qubits that are doing the calculations are not going to get exposed to the environment. And they do it by built-in error correcting codes. The cool feature about this is that this error correcting code exhibits geometry in the sense that, right, I can ask a question about how entangled is this portion of the system with the rest. How entangled are these qubits here, say, with the other qubits on the boundary? The answer is that the amount of entanglement is proportional to the length of the curve that kind of goes round like this. So the geometry of the interior is controlled by the amount of entanglement on the boundary in this quantum error correcting code. This is how we want to build a quantum computer. It exhibits precisely the same connection between entanglement and geometry that we've just been talking about. And it's in that sense that the world in which we live, the space in which we find ourselves now, resembles that of a giant quantum computer. So with that, I will thank you and stop. Thank you.